What is an op-amp or operational amplifier? Op-amps are differential input amplifiers that are used in electronic circuit design. Modern op-amps are integrated circuits that are small and cheap and therefore find use in many applications. Op-amps have as a circuit component 3 terminals, 2 input terminals and 1 output terminal. Of course, in reality 2 more terminals are needed in order to supply power to the op-amp, 1 positive voltage and 1 negative voltage terminal. So to start off with, we will speak about the ideal op-amp. The ideal op-amp has an infinite input impedance and a 0 output impedance. Furthermore, the ideal op-amp should have a gain whose value is very large and ideally infinite. What about the bandwidth? The bandwidth of the ideal op-amp is also infinite. The gain should be constant down to 0 Hz frequency and up to infinite frequency. This gain is called differential gain for obvious reasons and is also called open loop gain. The reason why it's called open loop gain will be more clear later when we start understanding the closed loop gain. So to sum up, overall op-amps are components with 3 terminals, 2 inputs and 1 output that have infinite input impedance and 0 output impedance, and also a really big, almost infinite open loop gain. So the obvious question that comes into mind when considering a component with infinite gain is, how are we going to use it? The answer is simple. In all occasions, almost all occasions, the op-amp will not be used alone, but will be used in a closed loop configuration. That's what we're going to see next. There are 2 basic closed loop configurations. The first one, where the input voltage is applied to the negative input terminal of the op-amp, is called inverting configuration. The second one, where the input voltage is applied to the positive input terminal of the op-amp, is called non-inverting configuration. In both cases we are applying feedback to our circuit in order to limit the gain. The first configuration that we will examine is the inverting configuration. Here you can see the basic circuit that consists of the op-amp and 2 resistors, one in the input and one in the feedback. Let's take a closer look at this circuit. First of all, in order to examine it, we have to note that in an op-amp, the voltage in both terminals, input terminals, is always equal. In this specific circuit, because the positive input voltage is connected to ground and it has a voltage of 0 volt, the negative input voltage has also a voltage of 0 volt. Now let's check the resistance R1. On its left side it has a voltage of V in. On its right side it has a voltage of 0 volt. From Ohm's law we know that the current I1 that flows through this resistor is equal to Vi minus 0 divided by R1, which is equal to the I divided by R1. As we have already mentioned, one of the basic characteristics of the op-amp is that its input impedance is infinite. This means that the current cannot enter through the terminal inside the op-amp. So there is only one path that the current can continue to, and this is feedback. Since the current that flows through the R2 resistance is the same, I1, we can use Ohm's law to find the output voltage VO. I1 is equal to 0 volt on its left side minus the out on its right side divided by R2. We already know though that I1 is equal to the in divided by R1. So the in divided by R1 is thus equal to minus the out divided by R2, and therefore the out is minus the in times R2 divided by R1. This equation can be used when we have an inverting configuration, and usually it doesn't have to be proven. The second closed-loop configuration that we will study today is the non-inverting configuration. Here, the input signal is applied to the positive input terminal. You can see on your screen the basic circuit of the non-inverting configuration. The approach that we will have in order to examine this circuit and find out what the output voltage is the same that we had in the previous one. So, first of all, the voltage in the negative input terminal will be V in, since we have already mentioned that the input terminals of the op-amp have always equal voltage. If we now examine the input resistance R1, we can see that the current that flows through it, I1, will be 0 minus the in divided by R1. Given that the input impedance of the op-amp is infinite, the same current that flows through the resistance R1 flows through the resistance R2. By applying once again the Ohm's law, this current, I1, is V in minus V out divided by R2. Solving this equation, we will have on the left side minus V in divided by R1 equals V in divided by R2 minus V out divided by R2, which means that V out divided by R2 is equal to V in divided by R2 plus V in divided by R1, and multiplying both sides with R2 and taking as a common factor V in from the right side, we arrive to this final equation: V out equals V in times 1 plus R2 divided by R1. I mentioned earlier in the video the open loop gain of the operational amplifier, which is too big or even infinite. The closed loop gain is defined as V out divided by V in. So in the case of the inverting configuration, the closed loop gain is the out divided by the in equals minus R2 divided by R1, and in the case of the non-inverting configuration, the closed loop gain is equal to 1 plus R2 divided by R1, based on the equations that we proved previously. So with this, we have covered the very basics of operational amplifiers. Thank you for watching. If you found this video helpful, put a like and subscribe to the channel.